Hello, everyone, and welcome to this math blog episode. Okay, and I want to update everyone that yes, I'm open to work and I have been sending out applications. And all I can say is that seeking opportunities this pandemic takes a lot of courage. And the experience, observations, and the risk assessment is worth celebrating for. Then I realized, guys, that as a public transportation dependent, I don't want to be a health risk or health hazard for my next employer and for my family here in Dallas. So I decided to defer first my on-site job applications, okay, and focus on my math tutorials and on my authentic learning. And yes, acquiring much joy from being on the bench in the job market is truly promising. Why? Because there is really such joy on being a teacher to our own self, to my own self, being an independent thinker and an authentic learner. So how are we gonna do it? And by the way, I would like to thank all of the parents who have been very supportive and who trusted me for my online math tutorials. So let me feature this article, what is authentic learning and how do I use it. So this is very useful because we all know that there are a lot of online resources. You can learn a lot of things online. So we have to be focused and well planned. Okay, we need to know ourselves so that our authentic learning will be always engaging and creative, okay, as you move along. All right, so what are the guide questions? Okay, so the first question, this article is telling us the first question is what real world problems is relevant to you? Okay, it's relevant to us. And this might be too much, but with your time, with your available time, it's all worth it to have a glance and a grasp on all of these social issues. However, being a big supporter of church time and prayers, I can say that I can live the studying of the social issues, the studying of the plans and execution of the resolutions for the social issues to the experts, okay, because they have been watching and they have well-informed opinions. But yes, being a math enthusiast, I'm a big supporter on protecting our planet, and I'm a big supporter on having that joy of teaching math online. And the next question is, what are the family and community stories? Okay, so this way we would know what is important to us and what inspires us. You would know yourself, okay, by knowing your family and knowing your community. And yes, we have to be resourceful in order to make our authentic learning very engaging, as well as our online teaching. Okay, so please continue to join me as I share more stories of my being an independent thinker and an authentic learner. And in this vlog, we'll be talking about ellipses. So please watch until the end. It would totally be creative, fun, and artistic. And now let's start with our ellipse talk. And you might be wondering, how are we going to describe in a mathematical expression an ellipse? Okay, so yes, we have a blueprint equation for an ellipse, and it's x minus h squared over a squared plus y minus k squared over b squared equals to 1. So yes, we introduced hk as the coordinates of the center, okay, and a has something to do with the major axis and b the minor axis, and we also have the c as the length, okay, between the focus and the center of the ellipses. Okay, so and the C length can be derived using this relationship. C squared equals A squared minus B squared. So let's have some visual. Okay, so I'll bring you to this another beautiful online resource from topper.com. Okay, so we'll have a technical walkthrough using this document. Okay, so here it is. Major axis will be the whole length of the ellipses. Okay, and then the minor axis would tell us about the width of the ellipses. Okay, so the length can be aligned to the x-axis. Alright, so we have our horizontal ellipses, and we also have the minor axis, okay, as the width, and it can be aligned to the y-axis for a horizontal ellipses, and if it's vertical, so the major axis aligns to the y-axis, and the minor axis is parallel, okay, to the x-axis. So horizontal ellipses and the vertical ellipses. Okay, so that's major and then minor axis, and we have the center, and then again the distance between the center and one of the focus is the C length. Okay, and then we have the A, okay, as half of the major axis. So if you want to get the length of the whole major axis, so that is 2A, and then if you just refer to the half of the minor axis, that's B, so the whole entire minor axis is 2B. Okay, so those are the parts of the ellipse: center, the foci, major axis, minor axis. Okay, and there's a beautiful symmetrical property for an ellipse. Okay, so if we will connect a focus, okay, to one point of the ellipse, okay, you will have a distance, for example, f1, p1. Okay, and if we were going to have another length, okay, for the second focus f2 and that initial point p1, okay, then we have a length f2 and p1. Okay, so you will going to connect the foci to one point. Okay, so you have two lengths, and if you were going to add those two lengths, okay, then we have a constant sum, okay, and that's 2A. So we have point P2 here, we have a point P3, so we connect P2 to the same two foci, and then you sum the lengths, okay, of these two lines. The sum of those lengths, okay, will be the same as the sum of the lengths when you have point 1. Okay, and again, if you have another point P3 here and you connect point P3 to the two foci, and upon doing so, we produce two lengths, two lines, and if you sum up the two lengths of those two lines, then we still have the constant sum 2A. So we will be showing that as true, okay, in a visual. So now let me show you that the sum of the lengths, okay, of the two line segments produced from connecting one point of the ellipse, okay, to the two foci. So we have two lines here. If we sum up the lengths of these two lines, okay, that will be equal to 2A. Alright, so that's an observed symmetrical property. So keep that in mind, okay? And 2A is the whole length of the major axis, right? Okay, so let's show that, okay, that it's very true. So again, we have f1 and then we have point, for example, q. Okay, so f1p plus f2p. So point P from the ellipse has been connected to the two foci, f1 and f2. And if we were going to dissect this whole major axis here, because the whole major axis is 2a, right? So we were going to equate, okay, this expression here to the length of the whole 2a here. So we were going to dissect the major axis into smaller line segments, and let's see if there's consistency. Okay, so f1 and o. Alright, so that's one line segment, and we have o to p. Okay, and then notice that f2p is a minus c. Okay, but this small line segment here is equal to this small line segment here. So if we add a small to this f2p length, okay, plus f1o length plus o2p length, we have covered the entire major axis, and that's 2a. Now let's consider that f1o is equal to c, O to P is equal to A, and yes, this small part here to be transferred over here is just A minus C. And if we will do our math here, and yes, we just have shown that it's equal to 2A. Okay, and moving on, we will now be showing the relationship of the C length, okay, the length of the center to one of the focus, C, okay, is C squared. The relationship is C squared equals A squared minus B squared, right? So let's show that, okay? So we have here a point in the ellipsis, Q, in the ellipse, I mean, Q. So F1Q and then F2Q, okay? And if we were going to add these two, all right, then that's actually equal to 2A, okay? But we were going to show here, okay, that F1Q, okay, is somehow an hypotenuse for this right triangle F1OQ, and F2Q here, okay, is another hypotenuse, and it is a hypotenuse for the right triangle F2OQ. Okay, now we will use Pythagorean theorem. So this is your x squared, this is your y squared, and this is your r squared. Okay, so getting the r, then that would be b squared plus c squared. I mean square root of b squared plus c squared. So I hope that you can see that. So we will now be substituting the length of the hypotenuse here, h, is equal to square root of b squared plus c squared, and that is the length of F1Q. So we will substitute. Okay, so we just now have 2 square root of b squared plus c squared, and we will do the math here. Again, this F1Q plus F2Q is equal to 2A. So we were going to equate this expression to 2A and then do the math further. Then we will get this relationship. Okay, c squared is equal to a squared minus b squared. Okay, please feel free to explore this with your learners. And now, what if c is equal to 0 and c is equal to a? So when are we going to have c equal to 0? When a is equal to b. So the half of the major axis and the half of the minor axis are equal. Can you see the picture now? Okay, so let's use the build of Tim to illustrate that. It's quite obvious, guys. So when your a half of the major axis and the half of the minor axis are the same, okay, this is our A here. Alright, so our B is 5, so we'll decrease this to 5. So yes, guys, it's so obvious. We will be able to form a circle. Okay, and then what if C is equal to A? Okay, so B is equal to 0. Alright, so when you say B is equal to 0, you don't have a minor axis. Okay, then if that is the case, then obviously we can form a line. So let me show that here. Okay, so B is equal to 0. So let's make it to 0. There you go. We have 2 points, and two points will form a line. And those 2 points are basically the 2 points of the foci, or the center and the foci. And now we'll be discussing a little bit on the derivation for the standard form of equation of an ellipse. And we'll be making use of the online resource of toppr.com. And in this website, we have an example or an illustration of a horizontal ellipse and a vertical ellipse. Okay, so we'll be making use of analytic geometry to derive the equation. Okay, and we'll be making use of the symmetric property of an ellipse. It states that when you connect, okay, the point of an ellipse to each of the focus, so you have lengths like length PF1 and length PF2. So if you're gonna add up those 2 lengths produced from the connection of point P to F1 and point P to F2, you will have, okay, the length of the whole major axis to A. Okay, so we have this statement. Alright, PF1 plus PF2 is equal to 2A. So again, we'll be making use of the distance formula, analytic geometry, partition plane. So this is 0, 0. So for our F1, that will be negative C0, and F2 will be C0. And you have a point in the ellipse P with the coordinate X and Y. Okay, so let's extract. Okay, let's use the distance formula. So we're gonna extract the X distance and the Y distance for each of the hypotenuse, because as you can see, we can create a right triangle, okay, with the hypotenuse PF1 and hypotenuse PF2. So we would just be extracting the X distance and the Y distance. So the X distance of PF1, as you can see, this is 0 to X, so you have X here, X length, and you have 0 to negative C, so that will be C length, okay? So, or value C. So X plus C is the X distance, okay, for this hypotenuse PF1. Alright, and then the Y distance, of course, Y squared. 0 to Y is Y squared. Okay, so in other words, PF1 squared is equal to X plus C squared plus Y squared. And get the square root of each side. So we have PF1 is equal to square root of X plus C squared plus Y squared. So we have extracted the X distance of this hypotenuse and the Y distance of this hypotenuse and applied the distance formula. Let's do the same for this length. This is again a hypotenuse. So the X distance of that one would be X, okay, minus C, the small part here, okay, is our X distance. Alright, and then our y distance again is y. So x minus c squared plus y squared is equal to pf2 squared. So get the square root of each side. So pf2 is equal to the square root of x minus c squared plus y squared is equal to 2a. And we were going to simplify everything. We will be getting this. Okay, I would challenge everyone to practice the algebra and simplify this. I did it just this afternoon and it was super fun. Okay, so after simplifying this, we'll be getting this line. Okay, and then again, square both sides. We'll eventually have this line. X squared over a squared plus y squared over a squared minus c squared equals to 1. And again, if you were going to recall, okay, another symmetric property of an ellipse, it states that the length of the origin, the center, okay, to one focus is called the C length, okay, is having a relationship with the length of the half of the major axis and half of the minor axis. That the half of the major axis A and the half of the minor axis B. And there's a relationship between those lengths, okay, C squared is equal to a squared minus b squared, and we have actually derived that a while ago, right? So if you will be getting the equation for b squared, it is simply b squared is equal to a squared minus c squared, and yes, it is in this line. Okay, so we would just be substituting a squared minus c squared with a b squared. And yes, we just arrived at our destination, the standard form of equation of an ellipse, which is x squared over a squared plus y squared over b squared is equal to 1. And now we'll be talking a little bit on directrix and eccentricity. Okay, so we'll be using the build of or Geogebra illustration of Kent. Okay, so we have here an ellipse, alright, and then we'll have, yeah, there you go, it's an ellipse, and then we have the foci and the directrix. Okay, so what is a directrix? Okay, so a directrix is basically an indicator, okay, on the eccentricity, okay, of a conic section. It's a circle, the ellipse, a parabola, and everything. So it's a line, all right. And if you want to know, okay, at what point in the x-axis or the y-axis can you draw the line of directrix? Okay, then we have this equation. So we just have to consider the point in the x-axis that is equal to a over e. So half of the major axis over is the eccentricity. And yes, the eccentricity is being measured as a ratio, okay, between the center, the length of the center to the foci C over the half of the major axis. So if we will derive that further, then in achieving or in determining at what point in the x-axis can you draw the directrix, then you can use the formula a squared over c. Okay, so that's the directrix. It actually gives you an information on how eccentric, okay, the ellipse is. So how do we measure eccentricity? Okay, so let's continue in this field. Eccentricity is actually the ratio when you compare the distance of the point of the ellipse and going to the focus, you have the distance here, there, and then you compare that to the distance of the point, okay, of a point in the ellipse to the directrix, okay, then you will get the eccentricity, okay. And the numerator is the distance between the point to the focus, and the denominator is the distance of the point going to the directrix. So PF over PB. So as we move P, okay, then the eccentricity never changes. Okay, just the parameters of the eccentricity or the ratio changes. Okay, the distance of the point to the foci and the point to the directrix. Okay, and the eccentricity, guys, will basically give us an idea on how wide the ellipse is and how narrow it is, or how long the ellipse is. Okay, so if we have zero eccentricity, then you are getting the circle. So basically, when you see that it is eccentric, so it's like normal, we're getting a circle. And then as the circle is getting narrower, then the eccentricity increases. Okay, and the directrix from the center is moving away from the center and far away from the center. Okay, so this is how it looks like when our eccentricity, okay, increases. All right, so the higher the eccentricity, the longer the ellipse and the narrower it is. The difference between the length of the major axis and the minor axis increases. Okay, that contributes, okay, to the increasing value of the eccentricity. So eccentric, okay, is not gearing towards being circle, so it is eccentric. Okay, and we have here another illustration. This is from KMAT 7. Okay, so as you can see, when our circle, okay, when our major axis is somehow the same as the major axis, and then 3.4, and we also have 3.4, for example, or 3, and this is also 3 something, 3.1, okay, like that. So you're arriving, or you're having a circle. Okay, and when the difference between the two increases, okay, or like that, okay, so it's getting longer and narrower. Okay, so in this case, our eccentricity is very high. The value of eccentricity is high. Okay, so I hope that you are now appreciating, okay, the concept on eccentricity and directrix. It's telling us on how eccentric the ellipse is, and how far the directrix is from the center. So if you're getting a circle, then it's at the directrix is at the center. And then as the eccentricity increases, so the major axis, the difference between the major axis and the minor axis increases, so the directrix is moving away from the center, okay, and your ellipse is getting longer and narrower. Okay, and now let's get artistic and creative, and let's apply what we just learned about an ellipse. So you might be wondering, why are we studying an ellipse, or why do we need to know how to draw an ellipse? So basically, an ellipse as a shape and a geometric figure, it can be seen in nature. And yes, as an artist or observer, it's nice to have a good sense for shapes and colors, and to have a good sense of perspective for our composition. Like, for example, on this one. Okay, if we want to achieve this reference for artwork, we can say that there is an ellipse for the torso. Okay, and if we will consider the torso and the head, there's another ellipse. So in studying the distance, okay, of the torso and the head, then we can draw ellipses to achieve that kind of distance. Okay, and with the help of ellipses, then we can compose our artwork pretty much well. Okay, and the same here. Okay, if you want to know the distance between these two persons, then we can just consider the ellipses. Okay, and having a good sense of distance, proportion, and symmetry. Okay, and we have a material here, a good blog, alright, by Rachel Shirley. Okay. Alright, and it's actually telling us, or it's trying to document, alright, what she learned, okay, in practicing or in drawing ellipses. So how to draw ellipses in a simple way. Alright, so with these suggestions we can apply, alright, and practice drawing some ellipses in your artwork and consider these suggestions. Okay, so there are some rules also. And I have a very interesting material that I also want to share in this blog. It is an application for the equation c squared is equal to a squared minus b squared. So it's telling us a relationship between the minor axis, the major axis, and the length, or the distance between the center and the focus. Okay, so how to draw an ellipse. So you have a Cartesian plane, derive the A, derive the B, and with the A and B being considered, we can determine the focus, the foci, and then have some strings, okay, and draw those set of points for an ellipse considering those two strings being attached to its respective focus. Okay, so that is really c squared is equal to a squared minus b squared in action. Alright, and we also have some materials here that is basically telling us that in nature there are really a lot of ellipses. So football, the Earth's orbit forms an ellipse. Okay, there are a lot of architectural buildings in the form of an ellipse. It's an elegant design. Okay, and lastly, if you have a good sense of symmetry or perspective in terms of ellipse, okay, then it will be easy for you to study the derivation of the volumes of ellipsoid. Okay, so in this YouTube video, okay, it's really trying to discuss, okay, the symmetric properties of an ellipsoid. Alright, so thank you so much for watching after this part. I hope that you enjoyed this video as much as I did in making it. I'll be sharing all of the links, okay, that has been shared in this blog in the video description. So continue supporting my channel, and I'll see you in my next vlog. Bye!